So let's see this in action with an example. Jessie has a superannuation scheme with monthly instalments of $600 and an interest rate of 7.8% per annum, that's per year, and it's compounded monthly. Now, straight away I can see from my work on compound interest that I'm going to need to change the interest rate from a yearly rate to a monthly rate. So that's the first trick that I've spotted. Now I need to find the value of her account after 10 years. All right, the first thing to do, let's deal with this interest rate. 7.8% per annum is how much per month? Well, we need to just divide this by 12. And when we divide it by 12, we get 0.65% per month. Now, think of what we're going to do with this. We need to work with the whole concept of compound interest. And remember, our compound interest formula says we take the principal, we do 1 plus the rate, and we raise it to the power of n. Now that's involved here. What is our rate? Well, 0.65% means 0.65 out of 100, doesn't it? So we need to actually divide this number by 100 to turn it into a decimal. So what we'll actually have as our rate is this. I've just added 2 more jumps of the decimal place in here. Now, I always, just to make sure I don't mess it up, I always look at my rate and just double check that it makes sense. These are tenths, these are hundredths. So if I had, say, a 1 here, that would be 1%, 1 in the hundredths column. And I've got less than 1%, so it makes sense 0.65%. I can see I've got my decimals right. But I always just check that to make sure it makes sense. And I don't stop with it as a percentage. Once I've divided my percentage by 12, I actually convert it into a decimal, because that makes it easy then to add it to my rate and say I've got 1.0065. Now, what does this really mean? Well, it means that every time Jessie puts $600 into this account, it's going to grow. You're going to have the whole $600, one lot of it, but you're also going to have 0.65% of it on top of that. And that explains why every time interest is given, we need to multiply our $600 by 1.0065. And that's going to happen every month. And the number of months that we have, we're going to have this situation. So we don't actually need to use this formula right now, but the concept of this formula is really, really important, because every time our $600 comes in, we let it sit there for the month. It comes in at the start of the month, and at the end of the month, we let it accrue interest, which means we multiply it by this 1.0065. So let's have a look at how it works. Getting rid of this for the moment. All right, let's say at the end of the first month. Now I literally write this out, end first month, and then I'll write that that's my A1. That way later on I'm not confused about whether it's the start or the finish. Now at the end of the first month, Jessie will have already put the $600 in at the beginning of the month. So that's been sitting there for the whole month. So how big will it be now? Well, it will be $600 multiplied by 1 and a bit, and our bit being the 0.0065. That's how much money Jessie will have at the end of the first month. All right, end of the second month. Now I've got A2, and I probably don't need to keep writing that, but I'm going to come up with a formula for A2 and A3 to see if I can spot a pattern. All right, think what's happened by the end of the second month. This is Jessie's first instalment at the beginning of the first month, and at the end of the month, interest was accrued, it grew a little bit. So at the start of the second month, she has all of that money. So let's write down what she has. And I'm going to write it down without calculating what it is. I'm just going to leave it in that form so that I can spot a pattern. Now, what happens to all of that money at the start of the second month? She puts another $600 in, doesn't she? So we'll tell the story. She adds $600 to the account at the start of the second month. And then at the end of the second month, the bank says, all right, take everything that you've got, all of that, and we're going to award you interest on it, which means we're going to multiply it by 1 and a bit. And our bit is this. Does that make sense? So we've put the money in and it's got interest on it. In the second month, we've got the money that we had, we've added to it, we've put $600 in, and then at the end of the month, we've accrued interest. All right, now before we go on and do A3, can we tidy this one up a little bit? Well, I'm going to expand some brackets here, just the outer ones. If I do 1.0065 and I multiply it by both of the terms inside the brackets, this first one is going to become 600 multiplied by 1.0065 multiplied by 1.065, isn't it? Can I write that a better way? I think I can. Where's my duster? Here. I can say that we've squared that number. Does that make sense? And if I multiply this number by the other term, now I have this. So I've just expanded this set of brackets here. I've left the intermediate brackets. And now I've got two terms. And I can sort of see some symmetry. They've both got a 600 in them. They've both got this number. This one's been squared, this one hasn't. All right, let's move along and think what will happen in the third month. Well, as she enters the third month, she has all of her money from the second month. So in other words, she has all of that. Let's write it down again. Now, you might be feeling like this is getting a bit tedious, and it is a little bit, but it's important to tell this story carefully. We have that money. What does Jessie do at the start of the third month? She gets her $600, right? And then what happens to all of that money at the end of the month? It gets interest on it. So that whole amount, I put that bracket a bit early, but now it's there. That whole amount will get interest. How do we give it that interest? We multiply it by 1 and a bit. That's our bit. And now we've got some more brackets to expand. I'm just going to multiply this number here, which is outside all of those brackets, by each of the terms inside. How many terms are there? There's 1, 2, 3 terms in there. So I need to do each one of these 3 terms multiplied by this. So the first one, we can see that we're multiplying by 1.0065 again. So instead of being squared, it will be cubed. And if we multiply this term by another one of these, then now we will have that number squared. And if we multiply this by this, we can just write those out together like that. Now I've got 3 terms, nice and simple. At this point, I think I've got a few lines that are kind of working and other lines that are good. I like this version of my A1 formula. That's the only version I have. I like this second version of my A2 formula. The first one I made was just me thinking about how I could get a nice neat version of it, and that's the neat one. My third, this one I was working out A3, but then I expanded brackets and tidied it up, and this was the better version. Now, why was it a good version? Well, it's got a pattern in it. Look, each of the 3 terms has a 600 out the front, and each of the 3 terms has got a 1.0065. It's either cubed, squared, or to the power of 1. That looks like enough of a pattern to me. I don't think I need to find A4. I can now jump to saying, well, what's AN? All right, what would AN look like? Well, when we had the end of the third month, we had a 3 and a 2 and a 1. So at the end of the nth month, we're going to have an N and an N minus 1. And it's going to keep on going all the way down. We always finish with this term, don't we? Each of them had that in it. All of the terms have 600 in them as well. Have you noticed that? So really we could factorise and bring the 600 out the front of some brackets. To me that makes sense. So I'm going to put the 600 out the front of the brackets. And what am I going to have inside? Well, I'm going to have a large one of these. Like when I say a large one, I mean to the power of whatever number that is. And then I'm going to have a slightly smaller one. Let's say n minus 1. And then I'm going to have a slightly smaller one. I'm just going to put dot, 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 because I don't know how many there'll be. And it's going to keep on going down until I have one that's squared and one that's to the power of 1, right? So I'm just going to write the last one in because I'm sort of running out of space here. Actually, let's do the squared one and the one that's just to the power of 1 and close our brackets. All right, now, does this look familiar? Yes. In our set of steps, we said we wanted to build up a pattern by looking at the first 3 time periods. We've done that. Then we want to come up with a general pattern that will work for any number of time periods. We've done that. Then we want to convert our general pattern into one that looks even tidier. Now I can see that this is a bunch of numbers added together. It's a series. Is it geometric or arithmetic? Well, how do I get from one term to the next? They're sort of written the wrong way around, aren't they? We're normally used to looking at our sequences as starting with a small number and then going up to a big one. This starts with a big number and goes down to a small number. Could I write them the other way around? Absolutely. This is exactly the same as if I had the 1 here, the 2 here, and the n minus 1 here, and this could be the n. Because if I'm adding up a bunch of things, it makes no difference what order I add them. To me, this looks a bit nicer now. I can see that to get from one term to the next, I just need to multiply by 1.0065. And the next term, multiply by it again, you'll get the next one and the next one. All right, now, considering we know the sum of n terms is a, r to the n minus 1, over r minus 1. All right, we've got our 600 out the front here, multiplied by this geometric series. This is the series, okay? Now, if we look at this series, let's just consider, what's the first term? Well, the first term of the series is 1.0065, isn't it? This is the first term. It was kind of the last term, but I just wrote them around the other way because I think that made it easier. All right, what's the rate? Well, the rate is what you need to multiply by to get the second term. That's also 1.0065. That's easy. Do we have everything we need to use this formula? Yes. It doesn't matter that we don't have the n because we want a formula with n's in it. Okay, so now we need to just chuck this part of the sum to n formula in here because this is our geometric series just inside the brackets. So we have a brackets rate to the power of n, 1.0065 to the power of n, we don't know what n is, but that's okay, minus 1, over, now you could put that over underneath that whole thing or just this part or even the whole lot, doesn't really matter, because here we've just got 3 things multiplied together. Rate minus 1, well this is our rate. If we take 1 off it, it will just be 0.0065. And we've done it. This is now a nice, neat, tidy, okay, it's not that neat and tidy, but a very useful formula for the amount that we'll have at the end of any number of months that we want to investigate. All right, so now let's get to the point where we can answer our question, and we need to be careful with time periods here. We want to find the value of the account after 10 years. Well, we're working in months, so straight away we need to consider 10 years. That's 120 months, isn't it? All right, now so that I can keep this on the board, normally I'd just keep working down, but I'm running out of space. I'm going to rub out this top part here so that we can figure out what to put in our calculator here. We'll leave this here. So my next step would be, therefore, A 120 equals 600 times 1.0065, 1.0065 to the power of 120 minus 1. Careful when you put it in your calculator that you don't put the minus 1 up there in the power. Get out of your power and put a big minus 1 down low there, over 0.0065. Put all that in your calculator carefully and you'll find your answer, which is that Jessie will have, after 10 years, $109,256.94. So she's not quite ready to retire yet, but she's only been working for 10 years. And this is going to grow quite rapidly because it's compounding.